The next two theorems we're going to state without proof. There should be a proof, I believe, of both in the textbook. Theorem 4.4 is simply the chain rule, which again, another theorem you'll remember from calculus. It says that suppose f going from domain D into R, and suppose G goes from D prime into R, and very important, f of D is a subset of D prime. So in other words, f's image, the values that get mapped to when you plug in all these values of D, is going to be a subset of D prime. If f is differentiable at x naught, and G is differentiable at f of x naught, then G composed with f, derivative evaluated at x naught, is going to be G prime of f of x naught times the inner derivative, f prime evaluated at x naught. I imagine you all remember that. And the next theorem basically leads us into differentiating any kind of a polynomial. So theorem 4.5 says that for an integer n, let f of x be defined as simply x raised to the n power. And this function is defined for all values of x in the real line. Well, we may have an exception to that in one of the cases, one or two of the cases. F of x equals x to the n. Well, if n equals 0, then what do we have? F of x equals 1, a constant. So f prime of x is equal to 0. That would, after all, be a horizontal line if n were equal to 0. If n is positive, then we get f prime of x. We bring the n down, and then we subtract 1 from the exponent. And in both of these cases, I guess I should have said for all x in R, for all x in R. Now the next one is a little bit special. So f of x equals x to the n. Well, we know the derivative. F prime of x, just like above. But it's not for all values of x anymore. This is going to be for all values of x in the real numbers, with the exception of the number 0. And in case you don't remember why, let's do an example here. In each case, f of x equals 1 implies f prime of x equals 0. That's simple. The next one, f of x equals x to the 5th implies f prime of x is 5x to the 4th power. We remember that. And this last one, though, I'm going to choose a negative number, so let's just choose f of x equals negative x to the negative 5. So n would be in this case, n would be a negative 5. Well, f prime of x is equal to negative 5x, subtract 1 from negative 5, and we get negative 6, which can be written like negative 5 over x to the positive 6. So now, with the negative exponent for x, that's essentially putting x in the denominator. So now we can't have a 0 being part of the domain. So just a very subtle difference between number 2 and number 3, in that the domain of the derivative is going to be different.